Welcome back, everybody. We're looking at our next module. We're still looking at continuous values, but we're going to be looking at more than two groups at a time. So this is, very similar to an ANOVA type situation in classical statistics. The hierarchical Bayes approach really works well for this, and it helps us control those false positives. And I like to make sure that we're using real world data whenever possible. Sometimes we might simulate from a existing study, and in this particular case, we're going to be doing kind of both. We're going to simulate from it for a couple of the examples, working with this particular data set, and then we're going to also just use the summary data. Believe it or not, you can use the summary data even in frequentistic statistics. You can use the summary data when you're doing t-tests or you're doing ANOVAs. In fact, that's what allows us to do some forensic statistics. So forensic statistics is where we might be using stats to figure out if there was some kind of wrongdoing in a particular study. Part of my statistical practice involves that. One of the things that we'll do quite frequently actually is look at the summary stats, rerun them, and try to calculate the p-value and see if the p-value that we got matches the p-value that the authors report. You'd be surprised how many times we found cheating. It's kind of depressing, to be honest with you. But that's one of the things that we can do. It's one of the services that we provide my company. And there are other companies as well that do that. And it's like I said, it's kind of depressing, but it's an important service. So anyway, let's jump into this. The data we're going to be looking at today is from a developmental toxicology studies published by some scientists at the U.S. Environmental Protection Agency. They're looking at body weight post-weaning in some mice. I believe these were CD1 mouse. There it is. So these were CD1 mice. The study that we're looking at in particular is Lau et al. It's published 2006 in Toxicological Sciences. And there's a link in the reference to the paper if you'd like to go grab it and look at it for yourself. As I said, we'll be using the hierarchical Bayes model to go through and do our comparisons. Again, these comparisons are all going to be back against the control. And the question that that we're looking to answer is, I guess I didn't put that there, but here, let me put that in real quick. So our objective is, are any of the, and this is, I believe this is PFOA, are any of the PFOA dose groups different from vehicle with respect to body weight post-weaning? So we're in particular going to be looking at the 6.5 week time point. One of the other things that I did here is I did go out looking for historical data, and holy cow, that took me a while. That took a lot longer than I thought it was going to take, at least an hour. And finally, I found some data for CD1 mouse. There's some growth curve data from Envigo. And what took me so long to find this particular data was I was looking for any other kind of historical vehicle control data first. I knew that Envigo or Charles River, they'll have this kind of data. They don't necessarily have it on the time spans that we need. In this particular case, they actually report 6 week and 7 week. Well, Lau et al., they report 6.5 week. So we had to make a couple assumptions, and I'll walk you through those assumptions that I made in order to get the data from the historical data from Envigo to be comparable. What's nice about the Envigo data, though, is that there's 100 animals that they're reporting for. So they're reporting basically the growth curve for 100 CD1 mice. And the other thing that was kind of tricky is in their report, they're reporting 2 standard deviations. So of course we had to make some adjustments there. But anyway, I was able to get that data, make the adjustments, and get a pretty good historical control. So I'm really happy about that. Actually, that worked out pretty good. Again, in this case, we're only going to focus on the female data. So off we go. The first thing that we always do is we're going to load up our libraries. And one question that you might be having in your head, and maybe you've already asked me this, is Do I have to load all my libraries up at the top? No, you don't. You don't. It's a common it's a common thing that we do in computer science and coding is we like to load everything up ahead of time. Do you have to do it that way? No. Um, when you go into production code, that's going to be what is expected. So, or even in research code, if we were to do a code review, there are certain conventions, shall we say, that we adopt as coders, and this is one of the conventions. It's not uncommon for me to forget to load a library and then load it later on the analysis. And what I'll do is then I'll move it back up here to the top. So anyway, just wanted to make sure you were aware you don't have to load all of your libraries at once. This is, this code is typically run line by line. Now, if we were talking about a, an R script, you certainly have to load your libraries before you use a function from a library. That's true. And again, from a code review standpoint, it's a convention that you would have all these up at the top, but it's certainly, functionally, it's not required. I'll put it that way. Anyway, so we got our environment set up. We got the parallel processing set up for Stan. Next, we're going to try to interpolate this CD1 historical growth data. And again, you can go here to the Envigo website and you can see the data. The female data from the Lao study is 6.5 weeks, as I mentioned before. Envigo reports 7 weeks, or 6 weeks and 7 weeks. So more or less right now, the distribution that, if you look at the means and even the standard deviations for the most part are kind of following this linear track. So what we're able to do is probably just assume that things are going to be more or less linear between the two. And that's probably going to be good enough for what we're trying to do here. I did actually use an image analysis program in order to grab out where the means were and where the standard deviations or the two SDs, because they're doing two standard deviations. I got that divided by 2 to get one standard deviation. And so this is basically what we have. Again, they have 100 animals. We don't have the raw data, so we're going to use simulation to just take one sample from this and just work from there. Not exactly the best idea if you can avoid it, but if you can't avoid it, that's what you could do. To be honest with you, when I'm in these situations, this is where you start seeing things like bootstrapping. So it would not be uncommon for me to actually run this kind of analysis maybe 1,000 or 10,000 times, which gets really computationally expensive, but it's only computer time. It's not my time. So I don't feel that bad doing it. And then what we will do if we run it that way, if we actually bootstrap it, it's kind of like with the hurricane models. If you're familiar with those, you get these things called spaghetti plots, and it's every model is a different line. It's kind of the same thing here. We might develop 100 different models because we're sampling 100 different times from here, and then it's kind of the ensemble model type approach where I've got 100 models. I'm going to then use those 100 models as my distribution. So that's one of the things that we can do. We're not doing it in this case. We're just going to take one sample. So here's our one sample. Again, we're using the normal distribution. We're doing random sampling. That's what the R is for. This says I want 100 samples. My mean is 30.5, and I've got a standard deviation of 6.6. I'm putting it into the object Envigo control, and I'm going to plot the histogram of that using the hist command. And there you go. That's what our histogram looks like for this particular draw from the normal distribution with those parameters. I guess one of the things that I'll mention is you can see that there's a wide spread here in terms of the body weights at our interpolated 6.5 weeks from Envigo. This is not actually atypical. What is atypical is seeing what we see in the Lao study, and now we'll go through that real quick. But the standard deviations in the Lao study are actually kind of tight. Now, given what they're reporting in the Lao study is actually standard error, so we need to convert those standard errors into standard deviations. And the easy way to do that is, I wrote out the formula right here, standard error times the square root of the number of samples equals the standard deviation. The problem is we don't actually know what the number of samples is. Lau et al. Tell us that it ranges from 4 to 11. So that makes this kind of tricky, okay? Because what we end up having is 0.6 times square root of, let's say, 4. And then 0.6 times the square root of 11. You can see it's kind of a difference, but I mean, is it really that big a deal? Not entirely. It's not like a deal breaker or anything. I'm gonna make the conservative assumption that they have 11 animals. Okay, I could have just as easily said that they only have 4, but in this case, I'm gonna give them the benefit of the doubt and say that they have 11 in every group, including their control. So here we go. That is the control standard deviation for the Lau et al. Study. One of the things I wanted to point out is, the controls for the mean have a mean of about 25 grams and standard deviation of, as you can see here, 1.99 grams. Let's compare that now to what Envigo is reporting. They have 100 animals in the Envigo report. They have a mean of 30.5 grams. That is 5.5 grams larger than what we're seeing for the mean for the Lau study. And the Envigo is reporting a much larger standard deviation, 6.6 grams. So that tells me that the Lau et al. Study is not replicating the population distribution very well. I would expect the Envigo data, because we have 100 animals being used, that is going to be much closer to what the population distribution is. What this means in the long run for the Lau study is it's going to be very hard to use it in order to make any kind of statistical inference. So that's one of the things that we need to think about. So anyway, what I'm going to do next is we're going to sample 11 animals from a normal distribution with a mean of 25 and a standard deviation of 1.99. So that is the Lau control data. And then I want to compare that to what I got from Envigo. I'm going to put this into a data frame, and then I'm going to use ggplot2 in order to plot the histogram so that we can see the two kind of side by side, if you will. Again, when we're building out this data frame, we got to create a couple of columns here. So the first column is our body weight. We're calling it body weight. And it's going to take the Envigo control vector and concatenate on the Lau control vector. The groups then are there's a group column, that'll be the second column. And we're repeating the Envigo label for the number of times that we have the Envigo control, which would be 100. And then Lau for the number of times that we have Lau, which is 11. That all goes into this data frame. We're calling the data frame control comparison, and then we're going to plot the histogram here. Let's do that. So you can see this red blob, that is the Envigo distribution. And then you can see this, I guess it's teal-ish color. That would be the Lau et al. Distribution. So what you see going on here is the Lau distribution is kind of on the lower end of normal for the Envigo study. Overall, the Envigo distribution is, again, quite broad. So we don't really see the Lau distribution as a good sampling of the population distribution. So our ability to infer anything within the Lau study back to population is going to be not very good. So that's kind of the big point I wanted to make. If you're starting off with vehicles that aren't great, well, then the rest of your inferences are going to be pretty crappy too. And so that's what we call garbage in, garbage out. So here I just want to show you what the what I would believe the population distribution to look like based on the idea that the Envigo data are more close to the actual population. So we're going to do that. We're going to do the same thing, except we're comparing the Lau distribution to the control population. Here's that distribution. Now, this is a slightly different view. You'll see I use position identity here for the histogram. Right down there is the Lau data. And again, you can see it does not represent well what the overall distribution is. It again is over on the lower side of the population distribution. So that just kind of shows a little bit more strongly what it was I was talking about. And the fact that the Lao distribution really does not look like the population distribution. Again, what that means is we're going to have a hard time, inferring back to the population distribution for this analysis. And I think I kind of say it here as well. We have to face the facts that most tox data and pharmacology to some degree use really small sample sizes that aren't likely to reflect the population distribution. And again, I don't want to hammer this too hard, but this is why a lot of us keep talking about the reproducibility crisis in toxicology and the fact that we're not entirely sure how much we can trust a lot of the tox data that's getting published in the journals right now. So anyway, we're going to move on. We're going to pretend that that the data are able to replicate the population. Again, we don't think that they can. I mean, we're dealing with small sample sizes to begin with, but we're going to put our blinders on and just pretend that this data is better than it really is. All right, so let's actually get to analysis because that's why you're actually here. So if you look at the table in the Lao paper, you can see that they've got different means for these different groups. This is 1 mg per kg, 3 mg per kg, 5 mg per kg, and 10 mg per kg. This is the mean for each one of those groups. This is standard deviations for each one of these groups, and we're going to assume they're doing 11 animals. We're going to sample from these distributions so that we have data to analyze. Next, we're going to run our hierarchical stand model. So we're going to look at, first, we're going to look at the more than two groups.stand file. So again, pretty straightforward, nothing you haven't seen before in terms of the blocks because we're always using pretty much the same blocks. Maybe transform parameters is new, I don't remember. But starting off with the data block, here we've got n, which will be our number of observations in total. We have n dose groups, that's the number of dose groups. We've got me not updating my documentation. Shame on me, shame on me. This one here, group ID, is the identifier for the dose group. So basically what we're doing is we're bringing in lots of data and we need to be able to tell Stan which measurements are in the same dose group. So that's what this does. And you'll see, we'll talk about that more on the other side. Y is our responses as per usual. Again, it is a vector of size n, right? Parameters, these are the things that we care about. Again, so I updated my documentation, but I didn't. So in the parameters block, these are the things that we're going to measure. Gamma is a vector of dose group deviation from the mean. And the mean that I'm talking about here is the overall mean. So this is the deviation from the overall mean, which is mu. We have sigma gamma. That is the standard deviation of the gamma coefficients. And then we have sigma y, which is standard deviation of the observations. So you might be wondering, what on earth are you doing? This is way, 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 way hugely complicated. Well, let me break it down for you. When we do an ANOVA, it's a lot like doing a regression model. And technically an ANOVA is a special case of what we call linear models. Regressions can be in the family of linear models. And what we're actually calculating are coefficients, and that is our treatment effects in the ANOVA. This gamma here represents that treatment effect. So we're going to have this overall mean. It's kind of like the intercept for the model. And then the level of the treatment effect is going to be in gamma. And so gamma is, how far does it deviate from the overall mean in this particular model? And there's going to be some kind of standard deviation for gamma. We're going to be calculating this transform parameter called y hat. And y hat is mu, the global mean, plus gamma, and then this group ID. So each one of the dose groups is going to have a gamma value. So vehicle is going to be group 1. 1 mg per kg is going to be group 2. 3 mg per kg is going to be group 3. 5 is going to be group 4, and 10 is going to be group 5. Okay. So we're going to calculate this y hat. And y hat, if you come down here, represents the mean for the observed values. And then we've got the sigma y, which is going to be the standard deviation of the observation. So the observation, so what we're trying to do is we're trying to figure out what y hat is going to be based on the y values, while also simultaneously figuring out what mu is, while simultaneously figuring out what these coefficients for gamma are. Sigma gamma, again, is the standard deviation of the gamma coefficients, and it's going to have this prior normal 6, 6, which if you want to know what that looks like, hist r norm. Let's do 10,000 so that we get a decent rendering, 6, 6. So it looks like that. Okay, so most of this data is going to be over here towards 6, but it could go out to 30, it could go out to negative 20. And actually, it can't go out to negative 20 because it can't go below 0, so it's a truncated normal. And then gamma is going to be centered at 0, and is going to have some values, some standard deviation sigma gamma. This is generic quantities. Again, this is to get us kind of an ability to figure out how valid our model is. We're actually not going to be looking at this so much this time. We're going to be validating our model just based off of the other data, the gammas and the mu's and stuff like that. So here we're building the data that goes into the data. I'm not sure why it's weirdly aligned. Thought I had that fixed from earlier. Let me fix that now. There we go. So what we're looking at here is the first thing is the number of observations we're looking at is 55 because we got 5 groups, 11 per group, so that comes out to 55. There's 5 dose groups, 4 PFO groups plus 1 control. And then this is the data. We have the control, we have the 1 mg per kg, 3 mg per kg, 5 mg per kg, and then 10 mg per kg. This is the standard stuff for running the model. So we'll go ahead and start that off. And we'll wait a little bit while it compiles. I had made some changes in the commenting, so it needs to recompile it one more time. And there it goes working. And there we go. You can see it's spitting out quite a bit of stuff here. We'll scroll down. So here we go. These are our gammas. These are our effect sizes. If you want to know how this all plays, I explain it down here. One thing you'll notice is that the y hat values for the same dose groups repeat. So let's look at that. So y hat 1 through 11 is all control. And that's because we have 11 observations. So these all repeat. They're the same thing. And that's because of our dose grouping. The gamma values are the effect sizes. That's what we really care about for this particular instance. So gamma 1 is equivalent to taking y hat 1 minus mu. Gamma 2 is equivalent to taking y hat 12 minus mu, and so on and so forth. So the effect size, or the size of the effects for each one of these dose groups is right here in gamma. Again, 1 is control, 2 is 1 mg per kg, 3 is 3 mg per kg, 4 is 5 mg per kg, and 5 is 10 mg per kg. So these are the values that we're going to end up using in order to figure out if treated is different from control. So the first thing we need to do is we need to figure out what our rope is. This is the same approach that we used last time. Here's our rope. Goes from negative 1.8 to about 1.9. And then we're going to calculate these difference distros and print them out. And we can just look at, are these 95% highest density intervals for the different dose groups within our rope. And again, here's our rope. That's within the rope. That's within the rope. That's within the rope. Okay, how about this one? Negative 1.66. Yes, that's within the rope. So all of these are within the rope. I think last time when I did it, I think this one was not within the rope. So sometimes depending upon how things just randomly occur, um, you're going to get different results. So based on this study, yeah, so we're going to have to update this. None of the dose groups are outside of the rope. So there are no differences in body weight compared to vehicle. Now then, as I mentioned, as you could see from before when I ran this, I did actually have a difference, which was kind of interesting. So now we're going to bring in some historical information. So we're going to combine together the Envigo data with the Lao data. So this is the Envigo data that we sampled. We're going to combine it with the Lao control data. And we're going to run this analysis again. And we're going to see if something changes. And again, the importance of what we're trying to do here is we want to make sure that we're using a good set of prior information that gives us a better sense of what the actual population distribution looks like. So here again, we've got some interesting stuff here, and we're going to figure out what our rope is. So our rope goes from negative 4.4 or so to positive 4.3. And we're going to see is anything outside of that rope. Nope, 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 nope. Everything is within the rope. And that's kind of what I expected because the standard deviation of the prior is so huge. So huge. It's a very, very large spread of data. So it's going to be very hard for anything to not be within it, especially given what we were seeing before. So the hierarchical Bayes also tends to shrink the estimates with more variances compared to estimates with less variance. So as a result, one of the things that we notice if you compare this result to the previous model is that the control population probably has less variance. So let's take a look at that. If we go up to gamma 1, a standard deviation of 2.17. Go here, scroll up quite a ways. And this is standard deviation of 1. So actually, it ended up ballooning out just a little bit, which is kind of interesting. So the last time I ran it, it shrunk a little bit, but that's okay. When you run things, different things happen. So as a result, what we're really seeing here is we don't really have this issue of the body weights being different in treated versus control. It's really all the same, and especially when we look at the historical data as well. Again, in terms of inference, there's not much we can say about this data because the variances in the body weights in the Lao et al. Study are suspiciously small. I'm not saying that they did anything wrong. What I'm saying is that it doesn't really match up with what I would expect for CD1 mice at this age. It also doesn't match up with what vendors are seeing for CD1 mice at this age. We would expect a much larger distribution. So most likely what's happening is in the Lao et al. Study, because they're such small sample sizes, they're getting really tight distributions that don't replicate what we would find in the population, and thus the inferences that they can draw are probably not at all accurate. So we're going to do another way to analyze the data, and in this case, actually, let me go back real quick because I bet there was. Okay, yeah. Okay, yep. So now what we're going to do, oh, sorry to make you all seasick. Now what we're going to do is we're going to analyze this data the more common way. Um, what you saw was one way of doing it. It's certainly valid to do it that way based on the individual data. It's kind of messy though. To be honest with you, and this is actually how we normally do ANOVAs anyways, we use summary data. We don't use the individual data. We actually use the summary data to get the different parts of the ANOVA table that we need. And then we do the analyses on those summaries in the ANOVA table. Kind of what we're going to do here. So we are going to actually not sample to get our data. Believe it or not, we are not going to sample to get our data, except for in the control situation. So what I'm trying to do is I'm trying to get summary information for these controls, but I need a way of combining together the information that we're getting from the Lao study with the historical information that we're getting from the vendor. And so this is how we're going to do it. We're going to use Stan to basically do a pretty straightforward Bayesian analysis to create a posterior distribution for the controls. So this is what we're going to do. Again, in the data block, we've got the n. This is number of groups. Excuse me, which isn't true. This is actually, again, I didn't change it here. This is going to be the number of individuals. Yn is going to be the, again, that's not true. This is going to be the individual control values. And in case you're wondering, yes, I did copy and paste from a different file. So that's kind of what's happening here. And I didn't update my my documentation. Mu is going to be our overall mean. Sigma is going to be our overall standard deviation. And actually, instead of saying overall, it's probably more accurate for me to say posterior, to be honest with you. That would be far more accurate. So we're going to have this posterior mean, this posterior standard deviation. This is our historical information from Envigo. Now you're going to say, now wait a second here. What you're doing here is you're adding in the Envigo data that you sampled, and you're correct, we are. What happens is, if I were to just leave the prior like this, and then not bring in the Envigo data and concatenate it onto the Lao data, what's going to happen is the Lao data is actually going to run the model, not the prior, because the prior has a larger standard deviation. But I know the prior is actually more accurate than what we have from Lao. So it's perfectly fine to say that this is what the normal distribution looks like, because what this is doing is it's saying this is what mu should be looking like, is values in this area, in this distribution. And then we're going to concatenate Envigo onto Lao to say, but this Envigo data is really what we expect the overall distribution to look like, and Lao is just part of it, and so we're going to concatenate that together. So we're going to run this real quick. And so right now it's recompiling the Stan code because I had made some changes to the documentation. Once it compiles that, then it'll go through, it'll load up the data, and then it'll run the MCMC, which it did just there. And you can see we have a mean of 30.12 and a sigma of 6.12. So this is now bringing in the Lao data into the historical data to give us a better sense of what the actual population data may look like. We're going to use this more than two groups v2.stan file. We had to change the stan file for this particular analysis because, again, we're using the means and the standard deviations that Lao calculated. So we need to restructure the file for that. So n here's the number of dose groups, yn is our estimated group means or effects, so the means. Sigma n is the standard deviation of the dose effect that Lau calculated. Here we've got mu, this is the mean across all dose groups. We have tau, which is the standard deviation between the dose groups, and eta, which is the unscaled deviation from mu by dose group. What we're going to do that's kind of interesting here is we're going to calculate theta. Theta's what we actually really care about. And we're going to do it by bringing in mu plus tau times eta. So we're going to multiply tau, which is that standard deviation between dose groups, by this unscaled deviation. So it's just another parameter that we can use to kind of scale tau on a per dose group basis. And so then eta is prior normal 0.5. And then this is the model that we're actually trying to fit for to calculate what theta is. And then we can have generated quantities that we can deal with if we want. So again, we're loading in just the means for y. N is 5 dose groups. And then this is the standard deviations. You can see I'm taking the standard deviation times square root of 11. Or sorry, the standard errors times square root of 11 in order to calculate the standard deviations. Everything else is pretty well the same. And now it should be running the Monte Carlo. And you can see it finished pretty quick. And again, the thing that we actually care about is going to be theta. And there's theta. And these theta values, again, are the effect sizes that we actually care about. These y rep values, this is for us to validate the model if we want to. We can see that, yeah, pretty much we're getting the values that we would expect, right? So we can take this 24.65, and we can look at this and say, you know, that's kind of not great. But remember that things are getting shrunk, right? So the empirical or the hierarchical Bayes, the hierarchical Bayes is shrinking things. So it's shrinking that that vehicle because it has much more variance than the other things. It's shrinking it down, okay? And that helps prevent us from getting any kind of false positive results. So it's a net good thing. We're going to save this environment because R keeps crashing on me lately. So I'm going to run this to save the environment. If you want to load the environment, so to load a saved environment, use the load function, and you would say load, and then file equals continuous more to groups.r data. And you could do that, and that would load it up. We don't need to load it up again because we just saved it. Again, we're going to calculate our rope, same way as we normally do. Going to calculate the difference distros. But this time, rather than going through all this, I want to show you something really cool. We can graphically show it like this. Ta-da! This is 95% highest density interval. So on this distribution, it goes from here out to here. If this blue line is inside this rope, it's not different from vehicle. So this is for 1 mg per kg. It's not different. This is 3 mg per kg. Definitely not different. Almost the entire highest density interval is in that rope. 5 mg per kg. Again, almost that whole thing is inside that rope. There should be 10 mg per kg. Again, a large portion of it is actually inside that rope. Now let's look at this code. This is kind of involved. So you can see here, I'm making that data frame the same way that we normally do, right? I've got my difference distro object. I'm just putting it into a column. I'm calling that column X. This is the ggplot function. Holy cow, it's huge. Goodness gracious, what's going on here? So this is the data frame that we're using, diff distro 10df, right? That's the first thing that we tell ggplot is this is the data I'm using. Come on, use it. This AES is the aesthetics. We're telling it that the X value for our histogram is the X column in the data frame distro 10DF. Okay. Here we're saying I want a histogram. Here we're saying give me a vertical line, and I want that vertical line to be at this x-intercept. This x-intercept, this line right here, is from our vehicle rope. Sorry, from our rope. I shouldn't call it vehicle. And it's this one right here. And you know that because I'm using this square bracket 1 to give me the lower part of the rope. Here again is my rope again. Here I'm saying give me the upper part of the rope. And so this is how we calculate that rope. So that's what these two vertical lines are, is the rope. I don't know why I have GM histogram in there twice. That's completely unnecessary. See, doesn't do anything. Let's just clean that up real quick. Man, what was I thinking? I know what I was thinking. I was thinking I was copying and pasting stuff. That's what I was thinking. Cleaning up my code in real time so you can see what it looks like. All right, there we go. I thought I got you. I did not get you. Now I got you. All right. Annotate. Annotate's so much fun. I love annotate. So annotate is how we're getting that rectangle built, shading in where the rope is. That's a lot of fun. I like that a lot. Oh, that's because I went down too far. That's in the ping line. Okay. We're going to get to that. I just showed you something before I wanted to show it to you. So we'll get back to that in a second. So this is how we make that rectangle, right? That's what this rect means, is we're going to make a rectangle. And I tell it where I want the different parts of the rectangles. So the X min, X max, Y min, Y max. So it's basically just the rope lines again, right? Nothing different there. Geom segment. This is new. You haven't seen this before. Everything else you've seen prior to this, you've seen before. This is new. This is new. Geom segment. This is how I'm drawing this blue line segment in every one of them, is geom segment. And here again, for the line segment, you have to tell it where to start on the x-axis, where to end on the x-axis, where to start on the y-axis, where to end on the y-axis. Okay, and that's what I'm doing right here. I'm telling it size 2, so it's kind of bigger than just a really thin line. And I'm telling it dark blue because I like dark blue. Annotate here is going to add in this 95% HDI label. So here, say annotate geom equals text. X value is -11, so it's starting off right here at -11, more or less. Or no, I guess the middle. Sorry, the middle of this is at -11. There we go. The Y value is at 3,000, so it's up here at 3,000. The label is what are the words you want to use, and then the color is the color you want. There you go. That's how you do that. Now, this is something I haven't shown you before. You can actually save these files. These image files. You can save them if you want. So here I'm going to save a ping. It's going to be a 300 DPI resolution. Again, what you do is you just copy and paste this text to make this plot that you want. So you write the ping command, and then you do this, and then you do dev off. Dev.off is important because that closes the file stream. Ping opens a file stream. So you give it the file name right here, you tell it the resolution you want, and then the size. I had to keep playing with this until I finally got the image to look the way I wanted to. And I'll show you what I mean. So if you were to do something like, I don't know, 600 by 600, right? And you're to run this. Let's do that real quick. That's a pretty ugly, graphic. It doesn't look very good. So what we need to do is we need to put this at a number that actually looks good. And I'm hoping you could actually see that. If you couldn't, when you run the code, change it to 600, and you'll see what I mean. It's not good. You can't read anything. But 2000 by 2000 I've tested and looks really good. it's a huge, it's huge. It takes up a lot of real estate on your screen. Huge, but it's pretty cool. So anyway, there you go. That's how we do the more than two group type comparisons with continuous data. Again, like I said, the way we normally do it starts right here at line 235. I wanted to show you those other ways because they're kind of a little bit more intuitive in terms of how you would do this, like in SAS or in R if you're doing a frequentist analysis. You'd start with your raw data and you put it into all these things. But what mathematically is happening in the background that you may or may not be aware of is it's getting summary information to populate an ANOVA table in the background that you don't see, or populating the t-test that you don't see, and then it's running the test based on that summary information. Well, that summary information, like I said, is already given to us in the paper. And so normally what we would do is we would actually just put the summary information into, and it'd be right here, into the Bayes analysis directly. We wouldn't be dealing with the raw data per se. And so that's just for your reference. But this is a pretty good way of doing a more than two group analysis, very much akin to an ANOVA. What we'll be working on next is something even more fascinating. It's going to be real world, extremely ugly data. So stay tuned for that. Thanks for watching this. And this stuff isn't easy. If you've made it this far, that's awesome. This is hard. This is very hard stuff. I hope the homework helps you out. The assignments help you out in practicing this and helps you kind of get the hang of this. You need to work on writing out the code yourself. Copying and pasting isn't a great idea. Muscle memory helps you develop this memory of what these commands are and what they look like and how they execute. So please, please work on actually typing it, not just copying and pasting it. That will help you as well. Think about what every one of these steps do. Think about what you're doing as you're running the different parts of the R code. Think about what is happening. Think about, in the stand file, think about what is happening in the stand file. I want you to deeply, deeply think about it. And if you do these things, this will come to you much easier and it'll come to you much more naturally. You can do hard things. I know it. This is hard. This especially is hard. This is like light years harder than what we were doing with the tumor stuff. Light years. I know you can do it. You're doing great. You've done great to get this far. Keep up the great work. Keep up the hard work. Keep on working. Thanks, everyone.